In this video, I'm going to sketch this curve, and I've already been given the derivatives. So the first thing I'm going to do is I'm going to find the domain. So the domain of my function is going to be the set of all x, where x is non-zero, because I can't have the denominator equal to 0. Next, I can consider symmetry, which can sometimes be helpful if I notice that the function is even or odd. This one is neither, so I have no symmetry. And now I'm going to see what my intercepts are. Now, x can never be 0. That's not in the domain. This function has no y-intercepts, therefore. Now, I can have that this is equal to 0. The function will be equal to 0 when x is minus 1. So I do have an x-intercept at minus 1, 0. Next, I'm going to consider asymptotes. So let's start with horizontal asymptotes. And to find my horizontal asymptotes, I would like to consider the limit as x tends to infinity of 2x plus 1, that's my function, over 3x squared. And of course, that is equal to the limit as x tends to infinity of 2x over 3x squared, as we discussed in class. And that is the limit as x tends to infinity of 2 over 3x, which is 0. So this tells me right away that I do have a horizontal asymptote at y equals 0. Let's do the other limit. And it's going to be the same. That will also be 0. So y equals 0 is a horizontal asymptote. Let's now consider vertical asymptotes, and I know that it's going to have a vertical asymptote at x equals 0. The denominator is undefined there, but I should still give my limits. So let's do the limit as x tends to 0 from the right of f of x. And let's do the limit as x tends to 0 from the left of f of x. So I'm going to do a little sign diagram for f. This is my function. And so its sign on this interval is going to be positive, and its sign on this interval is also going to be positive. That tells me that this limit is plus infinity, and so is this one. Next, I'm going to consider intervals of increase, decrease. So this is my derivative. And f prime x will be 0 when the numerator is 0. So when minus 2 times x plus 2 is 0. So that happens when x is minus 2. So that is certainly a critical number. Technically speaking, a critical number could occur when the derivative is undefined, but that point would have to be in the domain, and x equals 0 is certainly not in the domain, so that is not a critical number. So I have one critical number, that's x equals minus 2. So to get my intervals of increase, decrease, I'm going to do a sign diagram for the derivative. So on my sign diagram, I've placed my critical number and I've placed my vertical asymptote. So I know that on this interval, this is going to be negative. I could think of a test point like 100, and certainly I get a negative over a positive, and so that is negative. Moving to the next interval, the derivative does change sign. It becomes positive. And moving to the final interval, I see that the derivative is negative. So that tells me that f is increasing on the interval minus 2 to 0, and f is decreasing on minus infinity to minus 2 union 0 to infinity. Moreover, I can see that that critical number, x equals minus 2, is going to give me a local min because the function changes from decreasing to increasing at minus 2. So let's record that. So I have a local min at minus 2, f of minus 2, and throw that back into the function, and f of minus 2 is minus a sixth. Now for concavity, I need to consider the second derivative, and the second derivative will be 0 when x is minus 3. So f prime prime x is 0 when x is minus 3. So I need to do a sign diagram for the second derivative. And for that sign diagram, I've included that point where the second derivative is 0. That's a possible inflection point. And I've also included the vertical asymptote at x equals 0. So looking at the sign of the second derivative on this interval, it's going to be positive. And moving to the next interval, it's also positive. For instance, you could take minus 1 as your test point, and you can see that when you plug that into the second derivative, it's positive, and then it switches sign. This tells me that, in fact, minus 3 gives me an inflection point because it changes concavity there. Let's record our intervals of concavity. So this function is concave up on minus 3 to 0, union 0 to infinity, and it is concave down on minus infinity to minus 3, and I have an inflection point at minus 3 f of minus 3, and if I throw that in to the original function, that point is minus 3 and minus 4 over 27. Now I'm ready to sketch my curve. So I've recalled the relevant information. So first note, we had a horizontal asymptote at y equals 0. And I've labeled that horizontal asymptote in blue with a dotted line. I have a vertical asymptote at x equals 0, which I've also labeled in blue. And now I need to use the information that I'm given to sketch the curve. So first, I'm going to sketch some of these relevant points. All right, so far I've put the intercept minus 1, 0 here, and I have put the local min here, and I know that as x tends to 0 from the left, f of x tends to infinity. So I know that this function is doing this. It's also concave up on this interval, but then at some point in here, it switches to concave down, and it's going to hug that horizontal asymptote. So in here, I have my inflection point, which is minus 3 minus 4 over 27. That's my inflection point. Okay, let's just double check. So from the information I'm given, f should be decreasing until it gets to minus 2. And then after that, it's increasing all the way to 0. As well, it should be concave down till it gets to minus 3, at which point it switches to concave up. Now, for the rest of this graph, I know that f should be decreasing after 0. I also know that it's concave up. And furthermore, I know that as x tends to 0 from the right, it tends to infinity. So the remainder of the graph should look like this. And it should hug that horizontal asymptote.